I'm going to start the recording. We're going to take a look at section 5.2, which is exponential functions. We'll take a look at graphs of exponential functions and also how to solve exponential functions. All right, so I'm going to go to the shared screen. All right, and we're going to take a look at section 5.1, which is inverse functions. And when we talk about inverse functions, first we'll talk about inverse functions in relationships to graphs. And if we're looking at a graph, in order to determine if a graph has an inverse, or you may hear or see this one-to-one terminology. If the graph is one-to-one, that means that the graph will have an inverse. In order to determine if a graph has an inverse or if a graph is one-to-one, we use something called the horizontal line test. Now, in an earlier section, we looked at the vertical line test. And remember that vertical line test, it tests for functions. You know, you would draw a vertical line, and if the vertical line intersects the graph at no more than one point, and you have a function. The horizontal line test operates in a certain way, but it doesn't test for functionality. It actually tests if your graph is one-to-one. So here's the horizontal line test. It says that if you draw a horizontal line and it intersects your graph at no more than one point, then the graph is one-to-one. So here's what that means. If we take a look at example A, notice we have the blue line, which is our curve. If we apply a horizontal line, and if we get no more than one point of intersection, then the graph is one-to-one. Applying a horizontal line to this function, we notice that it intersects the graph at more than one point. It actually intersects at 3 points, which means that this graph is not one-to-one. And in other words, this graph does not have an inverse. If we take a look at example B, and if we apply the horizontal line test, so notice they actually applied the horizontal line test 3 times, right? If you look at the y sub 1 horizontal line, notice that it only intersects at no more than one point. If we look at y sub 2, it also intersects at no more than one point, as well as y sub 3. So for this second example, they just chose to draw 3 horizontal lines. Since it passes the horizontal line test, this graph is one-to-one. That means that this graph would have an inverse. Okay, now we want to actually deal with the compositions as they kind of relate to inverse functions. But what this means is if f is a one-to-one function, and if it's inverse, f circle g of x is equal to x, and g circle f of x is also equal to x. And that's actually shown in this example. We're given 2 functions. F of x is x cubed minus 1. Given g of x, which is the cube root of x plus 1. If we were to find f circle g of x, notice we get x. Right, we would substitute the g of x function into the f of x function. If we find g circle f of x, we would substitute the f of x function to the g of x function. And I'll also notice that it produces x as well. Okay. There aren't any questions on this. This is just part of the slides. Okay, just some actual proofs for inverse function. Okay, I'm actually going to skip over this slide for a second, and we will talk about okay, actually I'm going to go to the homework problems, and we'll take a look at a couple of homework problems. And in these specific homework problems, we'll be looking at graphs. And based on the graphs, we will apply a horizontal line test to see, in fact, if the functions are one-to-one. All right, so I'm going to go into section 5.1. And we'll take a look at problem number 3 and 4. All right, and I will generate a new example. And we're given this function, f of x is equal to the square root of 7 minus x squared, and we're asked to determine if the function is one-to-one. In order to answer this question, I'm actually going to graph this function using the graphing calculator, and I'm going to apply the horizontal line test. So remember, in order to graph any function, I'm going to go into y equals, and I'm going to clear out any of my functions, which I don't have. I'm going to put in the square root of 7 minus x squared, and I'm going to graph. Okay, so notice that this is the graph of a semicircle. I'm going to blow this up just a little bit. All right, so if I were to apply a horizontal line test, notice that if I apply the horizontal line test, let's say where my cursor is, it would pass the horizontal line test because there's no more than one point of intersection. However, if you can draw a line that violates definition, then the entire graph is not a one-to-one. So here's what I mean. If I were to draw a horizontal line here, it would actually pass. But let's say if I draw a horizontal line here, I would have 2 points of intersection. Since this horizontal line violates the definition, then this graph is not one-to-one. So if you can draw any line that has more than 1 point of intersection, then that graph is not one-to-one. All right, we'll also take a look at problem number 4. And in problem number 4, we're given a function, the absolute value of x plus 1, and we're asked to determine if it's one-to-one. Well, keep in mind what we know about absolute value functions. They form V-shaped graphs. So just by visualizing a V-shaped graph and applying a horizontal line test, I believe this function is not one-to-one. But in order to verify that, I'm going to graph it on the calculator. I'm going to go back to y equals. I'm going to clear out y sub 1. I'm going to put in the absolute value. So remember, the absolute value is within math. I'm going to scroll over to number, and absolute value is our first function. I'm going to put in x plus 1, and I'm going to graph. Right, so notice we have a V-shaped graph. If I apply my horizontal line test, I can find a horizontal line that intersects in more than 1 point. So this graph is not one-to-one. Okay. So when you're given these type questions on determining if a graph is 1 to 1, you're simply graph it in your calculator, right? If you don't graph it in your calculator, just remember from previous chapter we talked about algebra's common graphs, and we can use our knowledge of common graphs to determine if it passes a horizontal line test or we can graph. Okay, so I'm going to return back to the slides. Okay, we were here. And if we're given a function that is 1 to 1, how would we find its inverse? Well, here are the 3 steps. The first thing we'll do is we will interchange x and y. So wherever we see an x, we'll replace it with a y, and wherever we see a y, we'll replace it with an x. We'll solve it for y, and then we'll replace y with the f inverse of x symbol. So this is actually read as not f of -1 of x, this is f inverse of x. So that -1 superscript you see is actually the inverse symbol. So this is read as f inverse of x. So we're going to follow these 3 steps. I'm going to go back to our homework, and we're going to look at problem number 18. All right, and I'm going to generate. So here we're actually find the inverse of the 1-to-1 function. So this is sort of telling us that this is a 1-to-1 function for f of x is equal to x squared plus 8 for x is greater than or equal to 0. Okay, first of all, let's talk about this function for a second. If I were to graph x squared plus 8 in the calculator, notice that I'm going to stretch this out just a little bit. I'm going to go into Window. I want to go to Y max, and I want to change that from 10 to about 30. I'm going to regraph. And if we were to apply a horizontal line test, it would fail for x squared plus 8. But notice that there is a restriction on the graph. We only want the values of x that are greater than 0. Excuse me, that are greater than or equal to 0. So I'm going to actually graph that with my calculator. So the first thing I'm going to do is I'm going to put this x squared plus 8 in a set of parentheses. All right, and we did this when we were looking at, when we were graphing piecewise defined functions. I'm going to put in my restriction for x, so I'm going to put another set of parentheses. I'm going to go into test. I'm going to find greater than or equal to 0. So now just watch what happens when I graph. When I actually graph the function, notice that it does not display the U shape. It's actually half the U shape. So if I were to apply a horizontal line test, it would actually pass with this restriction on the domain. Okay, so that's not actually a part of this problem, you graphing it. I just want you to see that this is a 1-to-1 function only because we only want values for x that are greater than or equal to 0. So that would allow this function to pass a horizontal line test. All right, so I'm going to go back to the document count, and we're actually going to work out this problem. So we're asked to find the inverse and this is 5.1, number 18. Given f of x is equal to x squared plus 8 for x greater than or equal to 0. All right, so we're asked to find the inverse for f of x equal to x squared plus 8 for x is greater than 0. So remember, there were 3 steps. Before I apply any of the 3 steps, I clearly want to write out x is x and y is y. So remember, in function notation, we let f of x equal to y. So I'm simply going to rewrite this f of x as y is equal to x squared plus 8. All right, so that's our very first thing I'm going to do is actually pull out an x and a y. Now I'm going to apply the 3 steps. The first step was to interchange x and y. So here's what that means. Wherever I see a y, I'm going to interchange it with x. And wherever I see an x, I'm going to interchange that with y. All right, so I have x equal to y squared plus 8. Now I'm going to solve for y. Right, so in order to solve for y, the first thing I'm going to do is subtract 8 from both sides. So I have x minus 8 equal to y squared. I want to solve it for y, not for y squared, so I'm going to take the square root of both sides. To the square root of x minus 8. Right, so I solved it for y. The third step says to replace y with the inverse. Because remember, this is not actually y, because in the first step, we sort of interchange x with y, so this is actually x in disguise, not a y. So I'm going to replace this with the f inverse symbol. All right, so we have f inverse of x is equal to the square root of x minus 8. All right, so I'm going to put that in. Notice they already give us the inverse symbol. This is the square root of x minus 8. All right, I also want to backtrack, and we'll take a look at problem number 8. Okay, so we're taking a look at determining if a graph is one-to-one. We took a look at how to write the inverse of a function if it's one-to-one. We'll take a look at a relation. Now remember that a relation is just a set of ordered pairs. So here in this relation we have 4 ordered pairs. And we're asked to determine if the relation is a function. We're also asked to determine if it has an inverse. So in our relation we have -3 comma 1, -2 comma -4, -1 comma 6, 5 comma -1. Okay. And I'm actually going to write this down on a sheet of paper, and we're going to do what's called a mapping to determine if our relation is a function. All right, so here is our relation. Now, in order to determine if this relation is a function, we want to perform what's called a mapping. So in this mapping, I'm going to take every element of my domain. So remember, the domain are all of our x values. So we have -3, -2, -1, and 5. And I'm going to take our range values. The range values are all of the y values. So we have 1, -4, 6, and -1. And I'm going to perform what's called a mapping. So here's what a mapping is. -3 maps to 1, -2 maps to 4, -1 maps to 6, 5 maps to -1. So there's this definition. A relation is one-to-one if every element in the domain, so those are all of our domain items over here, correspond to exactly one element in the range. Right? So a relation is a function if every element in the domain corresponds to exactly one element in the range. So here's what that means. This -3 only corresponds to one element, or to one thing, 1. -2 only corresponds to one thing in the range. -1 only corresponds to 1, and 5 only corresponds to 1. Another thing you can look for in short, if you do not have any repeating x values. Right? So if I look in my relation, I only have one -3, I only have one -2, I only have one -1, and I only have one 5. Since I have no repeats from my x, doesn't matter about the y, only my x, then this relation is a function. So if I go back to our assignments, okay, is this function one-to-one? And the answer would be yes. Okay, so just remember in short, if I don't have any repeating x's, it's one-to-one. If you have repeating x's, then it's not one-to-one. Now, how do you write the inverse of a relation? Well, if we go back to the steps, or the very first step when we were writing the inverse function, the first thing we had to do is interchange x and y. So that's simply what we'll do here. In order to find the inverse of this relation, I will simply interchange x and y. So my first ordered pair is -3, 1. I'm going to reverse the order. I have 1, -3. I'm going to separate these out with a comma. My next inverse point would be -4, -2. My next inverse point is 6, comma, -1. And my last inverse point is -1, comma, 5. I think I have everything in it correctly. So to find the inverse of a relation, you simply reverse your ordered pairs. All right, next we'll take a look at 5.2. In section 5.2, we will explore exponential functions. I'm going to skip the first slide briefly. And here's the definition for an exponential function. If a is greater than 0, right, so a would actually be the base of your exponent, and a cannot equal to 1, then f of x equal to a to the x defines an exponential function with base a. So now here's what's a little bit misleading about this function. The a that you see, that's actually a number. Even though it's a, that a can be any number greater than 1, basically. Right, there is a number here. Your variable x is actually in your exponent. Okay. So just to elaborate on that slightly, okay. So I'm just going to kind of title this, which is exponential. So I'm just going to write two functions. Y is equal to 2x squared plus 4, and y is equal to 2 to the x plus 4. All right, so we've been looking at functions like this so far. The variable has been the base, and that base was raised to some number. For an exponential function, notice that my variable is the exponent. So these are two completely different functions. This is y is equal to 2x squared plus 4, where x is the base, 2 is my exponent. So notice my base is a variable. And for this function, I have y is equal to 2 raised to the power of x. So 2 is my base, x is my exponent, plus 4. So the exponential function would be the second function. It's important to know what's exponential and what's not exponential, because the way you solve exponential functions is different from the way you solve other functions. All right, so here's our basic setup for an exponential function. I want to go into the homework, and we're just going to take a look at some graphs of exponential functions. So this is section 5.2. Okay, let me see. All right, so from section 5.2, this is number 2. So notice we have, I'm going to generate a similar question. Here we're just asked to pick the correct graph for our function, and we have y is equal to 1/6 raised to the power of x. I'm simply going to graph that in my calculator. All right, I'm going to go into y equals. I'm going to clear out y sub 1. And I'm basically going to enter it as I see it. I'm going to put my base, which is 1/6, in a set of parentheses. And I'm going to raise that to the power of x. And since I adjusted my x and y axes, I'm going to graph this by using zoom 6. And notice I get graph D. Now going a little bit more in detail with these exponential graphs. All right, I'm going to return to the slides. Okay, so these are actually twofold. What I mean by twofold is that here's the graph of f of x is equal to a raised to the power of x, but a, which is your base, is greater than 1. The function that we just graphed, our base was 1/6, which is less than 1. And so these graphs will take different shapes based on your base. All right, so we're looking at graphs or graphs of exponential functions with a base that's greater than 1. Right, so here's the function capsule. So f of x is equal to a raised to the power of x, where a is greater than 1. Notice this is the basic shape of our graph. And it passes through these specific points. -1 comma a to the -1st power. So whatever your base is, you raise that to the -1st power, and it'll pass through that point. These graphs pass through 0, 1, and they also pass through 1, a. Right, so just as an example, I'm going to go into y sub 1. I'm going to clear that out. And I just want to put in 5 raised to the power of x. Notice our base 5 is greater than 1. So our graph should take on this shape. All right, so notice as we read this graph from left to right, it increases. All right, now we'll look at the graphs of exponential functions where the base is in between 0 and 1. So when we graph 1/6 raised to the power of x, it took on this form. So notice that if your base is between 0 and 1, as you read your graph from left to right, it should descend or decrease, and it passes through these points. -1 comma a to the -1st power, 0, 1, and 1, a. All right. I'm going to go back to our homework assignments, and we'll take a look at problem number 6. So keep in mind all of the transformations we talked about so far, how to move a function up, you would add to the function. You can move a function down or shift it down by subtracting 2 from the function. You can move the function to the left. You can also move the function to the right. You can reverse it or reflect it across the x or y axis. So all of those transformations apply. Of y is equal to 4 raised to the x. To sketch the graph, f of x is equal to 4 raised to the power of x minus 4 using the techniques of transformations. All right, so I'm going to click on the graph. So now the way we graph is a little bit unusual than the previous graphs. Notice from my math palette, I have the quadratic tool if you're graphing a quadratic equation. You have the cube tool if you're graphing a cubic equation. You have the log tool if you're graphing a log equation, which we're going to talk about in the next chapter. Excuse me, later in this chapter, we'll talk about logs. And then we have this exponential tool. So I want to use the exponential tool because this is an exponential function. Now, once you click on the exponential tool, no matter where you click, it's always going to give you this basic curve. All right, so the basic curve comes from an exponential function whose base is greater than 1. Okay. So notice that it gives us the base, which is 4. The -4 would actually be a vertical shift down by 4. So the only thing I want to do here is I want to make sure my base is correct. My base is 4, and I'm going to shift it down 4 places. I'm going to save that, and I'm going to change. All right, so just remember, if base is greater than 1, right, that graph would increase. If the base is less than 1, then the graph would decrease. Okay, now I actually want to go back up to the slide I skipped over. And these are some additional properties of exponents, and these will serve us when we're trying to solve some exponential functions. Okay, we're going to learn 2 methods to solve exponential functions. The first method is what's called the change. We'll drop the base. We'll use the drop the base method. In some problems, you can't drop the base, and you will have to use another method called a type 2. We'll have to use another method to solve an exponential. So in particular, I want to take a look at this additional property B. It says that if a raised to the power of b, so notice that a is my base and b is my exponent, is equal to a raised to the power of c. So here again, a is my base and c is my exponent. If I have the same base, I can drop the base and set my exponent equal. So this is the drop the base method we'll use. We'll take the exponential function. We'll try to make our bases the same, and once our bases are the same, we can drop the base and solve the exponent. All right, so here's a look at how that works. All right, we'll take a look at problem number 3. We'll also take a look at problem number 9. All right, so here's problem number 3. We have 36 raised to the power of x is equal to 6. And just as in any other equation, we want to solve it for x. All right, so we're asked to solve, and this is 5.2, number 3. We have 36 raised to the power of x is equal to 6. All right. And whenever you're asked to solve these exponential equations, the first thing you should do is try the drop the base method. So my rationale here is I want to try to make everything a base 6, right? Because here I have a base 6, and I can actually rewrite 36 as a base 6. So I'm going to rewrite 36 as 6 squared. So remember, that's still raised to the power of x is equal to 6. So remember that 6 has an understood exponent of 1. So I'm going to just write 1 here. For my rules for exponents, when we raise a power to a higher power, our operation is to multiply. So I can rewrite 6 squared raised to the power of x as 6 raised to the power of 2x is equal to 6 raised to the understood first power. Now that I have like bases, I can drop my base and set my exponents equal. And now I'll solve for x. So I'll divide both sides by 2, so x is equal to 1/2. So that means if I were to take 36, and I'm going to use this calculator, and if I were to raise that to the 1/2 power, notice I get 6. Right? So solving for x, we see that x is equal to 1/2. All right, I also want to take a look at problem number 9. All right, so here again we have an exponential function. 4 raised to the x minus 3 is equal to 16. All right, so this is 5.2, number 9. We're asked to solve 4 raised to the x minus 3 is equal to 16. All right, so here again, we're going to try to make our base 4, right? Because we can rewrite 16 as a base 4, and we also have a base 4 on the left-hand side. So I'm going to write this as 4 raised to the x minus 3 power. I want to rewrite 16 as 4 squared. Since I have like bases, I can drop my base and set my exponents equal. So I have x minus 3 equal to 2. I can solve for x by adding 3 to both sides. And I have x equal to 5. All right, so for our last example, x is equal to 5. All right, so I'm going to stop the recording.